Yeah, so my name is Dustin Leverman. I work at Oak Ridge National Laboratory, and I was going to be giving you all a storage site update. So it's not just specific to what we're doing with Luster, but kind of what our storage ecosystem is looking like right now. It's not progressing my slides. There we go. So, and I only made 10 slides, but when I ran through this earlier, it went a little over 20 minutes. So I'm hoping I can kind of speak quickly. So at Oak Ridge, we operate systems in many different security enclaves. So as you can see, we have many different systems, and some of these boxes represent, like Frontier's a 10,000 node system, some it's a almost 5,000 node system. So some of these boxes represent significant capability. But you'll see at the bottom here, we basically operate in these three different enclaves that are all broken out based on security controls. So like we have one enclave that we call open, where you can access data with a password, for example, or a key. We have our moderate space where everything gets accessed. You have to have a RSA token. And then we have another enclave that is that we call moderate enhanced, and that can support both ITAR and HIPAA data. And depending on which enclave you're in, there's different, like I mentioned, like for example, in the moderate and enhanced controls, it's also a moderate enclave, but since we store HIPAA data there may be requirements for encryption at rest or encryption over the wire, or like, for example, if somebody goes to open a file, we need to have an audit log of this person opened this file at this time, So there's all these different controls in place depending on which system we're in. And you'll notice in this diagram that there's, we have storage resources that, for each of these enclaves. So if we look at what kind of storage capabilities we host, at the top of this chart here, you'll see, we have job term data. So like, for example, you'll see here that in the OLCF, our primary sponsor, the DOE Leadership Computing Facility, our Summit and Frontier systems all have node local storage. So you'll see, and usually the data duration on that tier is 24 hours, which is our longest job queue time. But as you'd expect, that's node local NVMe. So that would be our fastest tier of storage. And then our expectation would be that if users choose to use that tier, their data would end up being transferred over to our short-term data. And generally, all of these file systems are all of our Scratch file systems. And I'll go into some details on what these systems are here in a moment. But some of our enclaves have multiple resources. So like for the OLCF, we run Alpine, ARCs. So we have our moderate resource, our moderate enhanced resource, and our open resource. But in some instances, our resources are shared by multiple programs. And we have chargeback models to be able to support, if the BER customer wants a certain amount of flash space or hard drive space or archive space, they can buy into those resources. But then we also have some systems that are only used by individual customers. And those are strategic partnerships we have, like specifically with NOAA or the US Air Force. And so what you can tell from this too is that today, mostly the OLCF is our biggest user of our medium, long, and forever term data. Our strategic partnerships generally handle that on their own side. But these start to get slower, and you'll notice that you'll see like HPSS, and we have a new system called Themis that basically should handle the medium, long, and forever term use cases. And these use cases are important to us, and you'll see some of these are actually even overlapping. Where, like I mentioned, if users are using job term storage, we would expect that data to end up at the end of the job getting transferred to our Scratch file systems, and then if users, we actually have a purge policy on our Scratch file systems that, if the users don't move their data to more permanent storage, we will purge it for them. But so our expectation is that users will move their data into either HPSS or Themis. And we have different use cases for those. So basically, like we have, like I mentioned, the purge policy is 90 days. So if users want to keep this data, some of them may have a project that lasts 2 or 3 years and they expect to access that data again. So when you access that data and it's in our, and we consider it medium term if they plan on accessing it again in the next few years, like basically in the short term, which may change how the policy is applied on these HPSS and Themis systems. and long term is basically we know that they know that the users will know that they want to keep this data, but maybe won't necessarily read it right away. So there may be like a, if it sits there for 3 months, we may punch it from the disk tier, but we'll still have a copy on tape tier. And then forever term would be, you want to keep the data forever. And the reason I mentioned that one is that's actually a different use case where when you keep the data forever, there's some implications on what protections you need to have for the data. Like, so for example, for something that's actually truly considered archive, we would need, let's say that there's some kind of bug or something, and the disk tier gets eaten or the metadata tier gets eaten, like there's something that causes corruption. We would expect that there are mechanisms built into the resource where we could have a diverse backup of metadata and be able to restore all data on tape, because in theory that shouldn't have been impacted since the tape is not electrically connected. And yeah, I hope that makes sense. And something that we've been working on as a center recently is that there are changes taking place in the flash and tape spaces. As folks have probably noticed that there's been a decrease in the number of vendors of tape, but that does solve a specific use case that I was mentioning earlier for the forever term data. So we're trying to figure out how to realize the performance of flash in our ecosystem, and then also this Themis system I was mentioning here that actually exists in our open enclave, which is useful for our users in terms of being able to enable workflows, because like I mentioned, you can access those systems with passwords and not have to use RSA tokens, so it makes automation much easier. So
Dustin,
right now, yeah.
Dustin, sorry, can you go back to your previous slide?
Sure.
There's a question on Purge Policy. Could you mention how you implement that?
Sure. So today we purge on 2 of our systems. One of them, some of our customers, I guess, when they buy like the Air Force, they don't actually purge these systems. They handle that on their own. We do tracking to make sure if one user is using a significant amount of the resource, that we will let the customer know, but we try to keep those resources relatively low utilization. But on our large systems like Alpine, for example, or like F2, so with Luster, we have a mechanism where we'll do an LFS find, and we run it in parallel for different trees in the namespace. So we basically, at the root of the file system, there's a project, and all users belong to at least one project. So we'll run an LFS find for the different project directories, and then concatenate that data. And then based on that output file, we will we run the script. It's called Purge that will remove, before it goes and removes the file, it'll check the A time again. But basically we can configure it. 90 days is what we have configured today. And then on Alpine, our GPFS file system, we do something similar, but we use GPFS's ILM policy engine, which, I mean, today we have, I think it's like 6 billion files on Alpine, and we can walk the whole namespace and output it to a file in something like 3 hours. So it's very, very, very fast. That answers your question. Okay, so our production Scratch file systems that we have today, and we have for each of these, there's likely a test system. Usually when we put a system in and we actually treat it truly as production, we'll have a building block that looks identical that we can, it may be smaller scale too, but if we're not going to test in production a big change to Alpine. We'll test it on a single building block, and we can test it at small scale. So this is not everything. This is just our production systems. Like I mentioned in the other slide, and if you saw Glenn's slide yesterday, or Glenn's presentation yesterday, these numbers that I'm listing here these are the hero numbers. So this may not be exactly what users see. And also it depends, like if it's a Luster file system, for example, as it ages, it may be really fast on day one, but as this file system gets fragmented, the performance may decrease over time. But I just wanted to show, we have several different file systems. You'll notice too that we try to have as much of a homogeneous environment as possible, because it's easier on our system staff. So you'll see, ARCs and Alpine are built on similar ESS building blocks, and you'll see that F2, Wolf, and Storm and Cyclone are built on similar, DDN, SFA. We try to keep things as as homogeneous as possible. And something that I wanted to note here is on our storm and cyclone system that we run for the Air Force, this is a little bit of a unique system. It's actually two individual file systems that that are supposed to be basically copies of each other, right? So we've deployed them in a very high resiliency way where, you know, they have different UPSs that they connect to. They use different MSBs, like the main switchboards, like power sources to power coming into the lab. And also when our customer ships input data sets for their code, they ship to both file systems. If one's down, there's logic that handles making sure basically it goes into a Slurm queue, and the replication job will be launched when that file system comes back. And the same is true where after a weather prediction job is run, there's a replication job gets submitted to the Slurm queue to replicate the cycling data. So it's kind of, that's a different type of system than what we're used to running. This is more of even though we treat all these systems as production, that system's like a high resiliency production system due to the nature of the workload that's processed there. And then like I said, I wanted to present on the storage ecosystem, not just Scratch. So I guess I mentioned before, we have our HPSS resource. I don't know what story, it's been called HPSS for the namespace was built in 1994. Probably the next gen system will have a different name. But today, you know, it's 160 petabytes of tape, and that's the usable capacity. It's RAID 3+1, and it has about 22 petabytes of disk cache. And with HPSS, you can assume that disk cache is truly a cache. You can peg things to the cache, but generally speaking, that's just users right there. And they, if the cache gets full, it flushes it and punches it. And then we have this new system, Themis, that's IBM Spectrum Archive, which is basically, you have a GPFS building block that can use DMAPI to address tape as an external pool. And today that system is, we have 60 petabytes of tape, and I should have maybe said 30 here because that actually doesn't take into account the overhead of the replication. But so it's 30 petabytes usable. And then it has 10.2 petabytes of disk, and it's an ESS, so you should see all the performance of the ESS building blocks. All right, so I've talked about what we have in production today. I've talked about our Scratch and our archival resources. So this is our next gen. So as Frontier comes online, this is our next gen Luster file system. So this is the Scratch file system for Frontier. Its name is Orion. It's probably the largest, physically the largest system I've ever worked on. It's 50 cabinets. 45 of those cabinets are disk cabinets. There's one cabinet for management, and then each of these, you can see in this diagram, I tried to circle it in green, that there's 5 rows. And you can see down below, I have a diagram here of what one of those rows look like. And so we organize this system into, we call them scalable clusters, which is the smallest building block that can operate in isolation. So you'll see in this building block, there's Ethernet switches for booting all the OSSs. And you'll see there's MDS and router nodes here as well. The routers are used for routing traffic off cluster, since this Orion is actually connected to Frontier Slingshot network. In the past, we've had separate like InfiniBand networks just for storage, but this system's actually integrated directly into Frontier's network. And then you'll also see that if you're familiar with Slingshot's network architecture, it's built in Slingshot Dragonfly groups. And you'll notice here that there's 16 Slingshot switches. So each of these rows has its own Slingshot Dragonfly group. But what that works out to is, you know, we have these 40 MDS nodes. They're in a chassis, so they're shared. The NVMEs, there's 24 NVMEs in each of these chassis, and those are split in half basically. And we build these pools. I'll go into some details on that in the next slide. And then we also have the OSSs, and we try to name them such where we can tell by the name which enclosures map to which OSSs, which map to which row, and so there's locality implied in the naming. But so basically for each of our OSS nodes, there's going to be 2 HDD OSTs and 1 NVMe OST. So this namespace will have a significant number of OSTs. So I'll get into risks a little bit later, but there's some risks associated with that. And then total across the 5 rows, there's 160 router nodes, where one side is EDR InfiniBand and the other side is 200 gig Slingshot. All right. So the status of this system, it's currently physically installed, and we're working our way through acceptance now. I'll go into some more details on it. It's a 3-tier system. So we have a capacity tier that's 679 petabytes of, and it's formatted ZFS DRAID 2 11 DRAID 2 11D2S. Now these numbers, like Glenn mentioned, there's lots of considerations that need to go when you say a performance number, because mileage may vary. But for the capacity tier, our expectation for our hero number on a non-fragmented system, which HDDs are susceptible to fragmentation, or at least you'll notice the performance, all of them are, I guess, susceptible to it. But we're expecting around 5.5 terabytes per second read and 4.6 terabytes a second write. And there's almost 48,000 18 terabyte hard drives. And due to the timing of the landing of the system, those are PMR drives. We're also going to have a performance tier. This is the first time. So I mentioned earlier that there's some changes happening right now in the storage ecosystem. Like tape vendors are pulling out, flash is becoming less expensive. We're still not to the point where we can meet our capacity requirements. I mean, we have single jobs that can output 80 petabytes in a single job, right? So there's some concerns. We want to make sure the performance tier can keep up, but there's also, I'll get into the performance tier only being 11.5 petabytes could introduce some risks when we have some really large jobs. So I'll mention that. I'll go into that in a little bit more detail in a moment. The problem is that it's flash, as you know, is very expensive. And so we had to do what we could to meet our capacity requirements while also trying to build flash into the ecosystem, which introduces things like a policy engine and other things that I'll go into more detail in a minute. But like I mentioned, each OSS has 24 NVMe, so multiply that out by 450 or 225 building blocks. That's 5,400 3.2 terabyte NVMe's. And then we also have another metadata tier, which you would think, 10 petabytes of metadata is insane. Like, why would you need that much? Basically our plan, let's say we plan for 100 billion files, right? Like, so let's say that's 100 terabytes of space used. Why do we have 10 petabytes of metadata? The plan is to implement DOM and basically set a policy where maybe all files, I'll get to that in a minute, I guess, the details, but we want to leave files on DOM. And then also I'll talk about the performance tier striping here in a moment too. But there's about 10 petabytes of metadata capacity. And you'll notice here too, these would be the intention here, since these are such large drives, 30 terabyte drives, is it's not about the performance tiers. We're just trying to accelerate, basically keep data off of the OSSs, or keep client access. If we keep a lot of small files on metadata, we're hoping that will keep some of these requests away from the OSSs. All right, some more details. This file system is considered center-wide. So it's not a system dedicated just to Frontier, right? We have other analysis clusters that mount it. We have data transfer clusters that mount it. Our next gen system. So when there's an OLCF6 compute system, it will mount this. And also, something I didn't mention, I didn't put in the slides, is actually Frontier is also going to mount Alpine. So these large systems are not just not dedicated to these supercomputers. They are global, which doesn't introduce some complications when you have one system that went out to lunch and now the file system's hung up. But anyway, I don't need to go into that. The system's designed so that all components are redundant, everything except for enclosures. So we only have 2 enclosures per controller pair. So that's not with our RAID scheme, that's not enough to handle enclosure resiliency. And something that's interesting about, this is a HPE cluster store product. However, like I mentioned, it's very, very important to us to keep these systems homogeneous. If we buy a cluster store here and an ESS there and a DDN system here, it creates this very complex environment that's hard for us to manage. So we work very closely with our vendors, so that we use the Anchor for our provisioning systems, and we try to standardize all of our systems to use that. Same with Puppet, like that's our configuration management tool. And, we'll populate data into images and we will run against our Puppet instance. And even though, HPE Cluster Store's product today will use Puppet under the hood, we redeployed all ourselves. So we use our centralized resources of that our infrastructure team runs. And then also, the Cluster Store product also has its own monitoring subsystem, but we redeploy everything, not necessarily, and maybe sometimes we may glance at what they do and try to figure out if it's something that we want to monitor as well. But a lot of times we've been doing this a long time. So we have the ways that we do this. And the goal, I guess, of that monitoring, and I could give a talk just about monitoring. The goal of the monitoring is we want to know about problems before our users report it. So we actually have a pretty robust monitoring, and I should have mentioned telemetry here as well, but we have a telemetry system. So like I mentioned, we basically redeployed the Cluster Store product using our own cluster management tools, but really we're still building Cluster Store from the same recipe that the vendor is pushing. So like we use the RHEL version and RHEL kernel that they build because they may have a custom kernel. We use the ZFS RPMs, and their product uses a certain RAID config. We use that and all the tunables associated with it. Same with LNet and the high availability software, all the block device tunables. They may even have like for example, let's say they had a custom SAS driver that solved a specific problem that's newer than the one that's included in RHEL. Like basically, we're building this system as their recipe, but it is Cluster Store, but it's not quite. Like I mentioned before, the performance tier should be treated as a write back cache, and it's going to be that functionality will be implemented via a policy engine. Today, our plan of record is to use the HPE developed CDS policy engine. And basically, we're going to be setting our Stripe policy such to where PFL will, and I'm going to go into some details here on that in just a second, but we're going to be using PFL to implement that. And like I mentioned, we couldn't afford a very significant amount of flash just because of the pricing and needing to meet certain capacity requirements for our capacity tier. But basically, we plan on using the self-extending layouts feature just to avoid the performance tier from hitting eno space. So basically, if the performance tier gets full, it will new blocks will go to the capacity tier. So that's our plan. And like I also mentioned, we're going to be implementing DOM. So basically, we're still working on what exactly this policy will look like in production. But likely assuming something like 100 billion files, likely we'll be able to store something like every file under 512K or 1 megabyte will stay on DOM. And like I said, the reason for doing that, even though the DOM tier is not incredibly performant because of the low number of NVMEs, we're hoping that that's okay because these files are so small. And it's DOM is not necessarily about accelerating performance, even though it is. It's about avoiding communications with the OSSs, so letting the hard drives not thrash as much for lots of small files. So we're hoping we can accomplish that. And then likely the next stripe will be, let's say, the next 1 to 2 megabytes. And that will, like I said, all writes will be written to the performance tier, and then that will be via policy engine moved off. However, we were discussing potentially maybe the next 1 to 2 megabytes of the file never leaving the performance tier. That'll just, not of every file, I'm sorry. Files of less than 1 or 2 megabytes will just remain on the performance tier just to keep it off of the hard disks. And we have the capacity for it. We don't think it'll eat a significant amount of the performance tier. And then all data over that will eventually be migrated to the capacity tier. And like I said, we came up with this plan about 2 years ago. We're in the planning phase, and we need to revisit how Alpine, our current leadership class production GPFS file system, is used so that we can tune these numbers. And then, like I mentioned before, is that I guess I wanted our users to expect any read performance to be the performance of the capacity tier. So like I mentioned before, we're expecting 5.5 terabytes a second when the file system is initially formatted. That might get slower over time with fragmentation. But, depending on when the policy, if somebody writes something to the performance tier and they run again right away, if they're lucky, that might still be in the performance tier, but it may not be. So we're trying to set that expectation up front that, the point of this was to accelerate the checkpoints of our user codes. And then I mentioned this before, this is another spec, I don't know where to throw it in, but it's going to be, each of our nodes is going to be dual rail 200 gig slingshot 11. And then it's also going to be using the KFI LND, which is new. And I don't know, I'm trying to recall if NERSC uses that in production. I think they might with their new slingshot 11 upgrade. And I don't know exactly, but I think we're one of the first sites to be running that. All right. I hope I'm not running over my time. So Orion features and risks. I think I only have one slide after this anyway. So this system, I feel like is, I mean, there's the acceptance of this is going to be complicated. And I mean, it's not our first foray into this, but I know we'll make it through it, but there's a significant amount of new features and risks in this system. One of those is, and then actually, I think Livermore might be, since I made this slide, I should have updated this. I think Livermore actually does use ZFS D-RAID in production for one of their archive resources, but that's the only place I've heard of it being used at scale. So I'm interested to see what kind of issues we'll run into with that. It's a new network architecture, Slingshot 11. I think it is used in production. I think NERSC is moving to that, so this may be an old bullet. It's using the KFI LND, like I mentioned, NERSC might be using it as well, but I don't know how wide it is in the community. So at this scale, I don't know what we're going to run into. DOM, you know, we've been talking about this at the LWG for the last couple of years about what sites are using DOM. I know some started using it, some ran into issues and stopped using it. That is the plan of record of our system is to use DOM. So I'm hoping that if there are outstanding issues or low adoption, that hopefully we can, you know, work out some of those issues and make it more widely used. The policy engine, like I mentioned before, we're using self-extending layouts. And we're also, it's going to implement, again, you could I feel like I'm glossing through huge things of this system, but our plan is to use FLR. And that's, I don't know how widely that's used by the community, like in terms of functionality or performance. And honestly, most important part is reliability. So that's going to be interesting. It's also a risk. I mentioned before that, you know, this system is going to have 1350 OSTs. On our Atlas file system, it was Titan's Scratch file system. It had something like 1200 OSTs. And a problem that we had back then is that when users would stripe their data -1, which for some reason they would do, they would hit vmallocs and cause our MDSs to get overloaded and crash. And that was with a smaller number of OSTs that we have on this system. And my understanding from James Simmons is that actually this may be due to some new features landing. This problem may be exacerbated with newer versions of Lustre, because I believe that system was Lustre 2.8. So we'll learn a lot on the large number of OSTs. We're also going to be, like I mentioned before, have 40 metadata targets, which using LDiskFS, the tuning behavior. I mean, if I recall correctly, I'm trying to remember the exact numbers, but it's something like at 20 MDSs, your performance starts to degrade and almost maybe even flatline. So we're at 40 to be able to hit a decent DOM capacity. So we'll see at that number of MDSs and MDTs what we've tested with ZFS, but not at 40 MDSs or MDTs. We'll also be using multi-rail at scale, which is something we don't use on any of our production systems today. We do have multiple ports, but a lot of times that's implemented with, it might be LACP bonding, not dual rail. So that's a new feature for us. Another thing is, like I mentioned, it's a global file system. So it's tied into Frontier's network. So if Frontier is offline for maintenance, Orion needs to be able to stay online, right? So we're going to be relying on Slingshot Fabric Manager failover. So we have yet to test that yet, but the Fabric needs to stay online even if Frontier and Frontier's Fabric Managers are offline. And then also that I feel like the timing of this system is fortuitous too. If Lustre 2, so right now the system's booted with Lustre 2.15 RC3, so the 2.15 is not GA yet, but our plan is to accept with Lustre 2.15. So hopefully, if we do run into these problems with all these other risks, we can help pull those patches and upstream, to help stabilize the software, to help the community. I just want to mention briefly, so like I mentioned, Orion is going through its acceptance. I could probably give a whole nother talk just about acceptance, but we broke it into 4 phases. Right now, our hardware delivery and basic health is complete, and we have single building blocks built, and they're going through, testing individual drives, testing, you may run OBD filter survey against a building block, or there's lots of other tests that we're going to run on that self-test, just to test if a single building block is performant as like we would expect. And then we'll start a scale up activity, and then we'll do a full scale functionality performance and set of stability tests. But right now we're on number 2, phase 2. So I guess in conclusion, we have many different tiers of storage in our storage ecosystem because we have many different use cases. We have node local jobs where users, if somebody's doing something that's very random read heavy, that's something that we encourage them to use node local storage for. We're taking some risks, trying to get the best performance out of our scratch file system and leverage Flash. And DOM, these features that have been around for a while, and we're hoping will pay off. The risks will pay off for us. And then also, like I mentioned, we have these archival use cases where, not being electrically connected and being able to have not electrically connected, like taped media. And also, like when it's in the library, it's just sitting at rest in sheet metal for, but also being able to have a diverse backup of the metadata meets our archive use case. So we have a pretty complex storage ecosystem. And our installation is ongoing, and you'll probably, I'm guessing, hopefully next year at LUG, we'll give another talk about how acceptance went and talk through some of the issues we had there. Does anybody have any questions?
Yeah, we have a couple of questions, Dustin. So first one, and I don't believe you said this, but if you did, forgive me. Imran M asks, who is the vendor for the Orion file system?
Orion is HPE. It's an HPE cluster store product. Yeah.
Thank you. We also have a couple comments. I'll just read them out in case you have any feedback on them. So Cameron Har from Livermore mentions that in addition to the HPSS cache that you mentioned in your talk, they also recently started running DRAID in production on one of their systems in LC. And forgive me, I don't know what LC is.
Livermore Computing. It's there. We're NCCS. They're Livermore Computing. Okay, that's interesting. That's good. I'm actually glad to hear that it's being used more in the community.
Here's a question from. Forgive me if I mispronounce anyone's name. I'm sorry. And then A, do you use file system scanning tools like Lester or Lester change logs in production?
So the plan will, so I want to be careful answering that question because I don't know what I'm allowed to say about HPE's CDS. That's the policy engine we will be using. I will say that we do plan on using the changelog in production, and we, instead of using a tool like Lester, right now our plan is to parallelize using like we've been Rick Moore, like SARP's team, non-Jews, like those folks have been working on creating extensions for LFS find, and we're trying to, we want to use features like for listing the file system, for example. Like if we don't care about capacity and are just trying to create a list of files to purge, we can do lazy size on NDT and run LFS find, and it's very fast, and we can parallelize it. It seems to scale very well.